so we're going to get started. Welcome to Wyzant's Getting Ready for High School Chemistry. Tonight we are going to go into AP Chemistry. This session is for students that are starting AP Chem this year, so it's assumed that you've had chemistry already a little bit. So we're banking on that. So I'm going to go through each slide and explain everything. We're going over types of reactions, writing and balancing equations, chemical equations, and then stoichiometry. So I will do one example, or I will go over stoichiometry. This is a concept you probably learned in honors or regular chemistry last year, maybe at the end of the year. Maybe you didn't learn it because of last year's schooling. So I'm going to go over it briefly, but all of this stuff, I'm going to be teaching this as you've already seen this once. So hopefully it won't be too fast or too complicated. I'm going to try to simplify it, and I'll go through kind of like naming and writing compounds briefly. If you have questions, just drop them in the Q&A, and I will look at them throughout the slides, or I will get to them at the end of the slide if for some reason I don't catch them. So please feel free to ask questions. And we'll get started. So in chemistry, just a brief overview of generally chemical reactions, because that's what we're talking about tonight. Chemical reactions, what do they look like? What do they mean? What is all of this? This looks like a different language to some people. Hopefully you've seen something like this before. So what does this mean? So when we write a chemical reaction, we write these symbols here with like numbers and numbers here, subscripts, coefficients, the line here, and all of this means something. So if you visualize this, CH4, this is like 1C with 4 H's, 2 O2 molecules, so this is literally 1 and 2 O2 molecules, and then the arrow yields, so I'll talk about this in a second, CO2 and 2 H2O. So what is a chemical reaction? What does it look like? It's basically just a snapshot of what's occurring over time to these chemicals. So we can see here that the CH4 is breaking apart, the O2s are breaking apart, and they're kind of switching. And the C is bonding with the O, and then the H's from the CH4 are now bonding with the O's from O2 as well. So we're going to go into what type of reactions these are, how to spot them, how to write them, what each of these mean. So first of all, we call everything on the left side of a chemical reaction, we call these reactants. So these are what you're putting into the reaction to make it go or to form products. So reactants are on the left side of the equation, and they're in like this salmon color, pink color. And then the products are on the right side of the equation. So products are what are formed in the reaction, and overall, usually at the end of the reaction, this is what you have, are products. And then we have these. These are state symbols. So if you tuned into the webinars from last week, we kind of went over the states of matter. So they can either be solid, liquid, gas, or aqueous is another form of matter, not necessarily a state, but that just means dissolved in water. So in all of this case, this is a combustion reaction, which we'll talk about in a second, but all of these are in a gas state. So you wouldn't really see these very much, but in the reaction, but they're in a gas phase. So they're moving really fast. And then we have these numbers here, we call these subscripts. So these are the smaller numbers. So whatever element they're following is how many of that element there is. So for instance, the 4 is here, it's following H. So there's 4 H's in this case, and we can see that with all of these white spheres. And then there's 2 O's here, and 2 H's here. So the subscripts say individual elements, and then we have what we call coefficients, these larger numbers here, which go for the entire molecule that it's in front of. So coefficients show the amount of each particle or molecule, and they are the ones that are inserted to balance the equation. So remember, when we're balancing equations, which we'll practice in a second, we cannot change the subscripts in a balanced equation. We can only change the coefficients. So that's why it's a little bit difficult, because we have to put a coefficient in, and that will modify the entire molecule. So in this case, if we have a 2 in front of O2, there's technically 2 times 2 So there's technically 4 O's in this case. And over here, whatever this number is here, we multiply by all of the subscripts within the molecule. So 2 times 2 is 4 H's, and then 2 O's here. So the subscripts are what we can change. I'm sorry, the coefficients are what we can change. The subscripts are what we leave alone. And the subscripts are either from the name or depending on the charge of the molecule. So you might have remembered naming and writing ionic compounds. We'll go through that really quick. Okay, so types of reactions. This is something you probably did in Chem 1. So this will be a brief overview of types of reactions. This is important in AP because you need to be able to not only write reactions, sometimes you'll have to finish reactions. And so in order to finish them, you would have to kind of recognize the type of the reaction based on the reactants, and then you can finish the problem. Okay, so I'm going to go over this in the form of the type. So I'm going to list all the types of reactions, write the general formula, and then give an example. So the first type of reaction that we have is called a synthesis reaction. This is also commonly referred to as a combination reaction. I've heard it called that as well, but we call it synthesis. AP usually refers to this as synthesis. And this is very simple. So you're starting out with 2, it's basically 2 to 1. That's what I always say, 2 to 1. You're starting out with 2 elements and you're converting them into one compound. Or this can also be an element in a compound and you're converting it into one compound. So essentially you're starting out with more and you're ending with less. Everything is coming together, is bonding together, or is synthesizing. So an example of this would be magnesium with oxygen gas yields magnesium oxide. So this is an example of a synthesis. In this, if you didn't have this here, if you didn't see the product, you could pretty much assume this is going to be synthesis because there's nothing else that this can really do besides come together. You have 2 elements by themselves, so by default, this would be a synthesis reaction. Then we have decomposition, which is essentially the opposite of synthesis. So now we have a compound by itself, and then it's decomposing usually by heat or some sort of catalyst being added into its individual elements. So an example of this would be sodium nitride decomposing into sodium and nitrogen gas. This is actually the reaction in airbags. So we have this compound in airbags and it is catalyzed or essentially set off by a reaction when the car is smashed and it decomposes, and it's actually the nitrogen gas that fills up the airbag. So again, if you were given just this reactant in an AP exam, you could figure out, typically they don't talk about decomposition in AP as much, like they don't really have you finish reactions for decomposition. They're probably the more difficult ones to finish because it's not like cut and dry every time. This one is kind of simple, but typically you would look at this and you would say, okay, that's like, obviously there's nothing else it can do except for break apart if it's going to go through a reaction, so this must be decomposition. And then we have the replacement or displacement reactions. So single replacement is also referred to as single displacement. They're the same thing. This is when you have a single element and then a compound and something switches. So usually the cation or sometimes the anion. So if your single element is a cation, meaning it's a positively charged, typically metal, it will switch with the other cation that's part of the compound here. Or if A is an anion, then it'll switch with the anion in the compound here. So always remember when you're writing ionic compounds in the end, they must be cation, anion. So you can't switch an anion with a cation because then you would have both like anion, anion or cation, cation. So an example of this, and a lot of teachers do this in a lab, this is actually kind of fun to do. You can like turn a penny kind of like silver, but you can put copper. So like you can put a copper, penny has like a slight copper layer, but you can put a copper penny in a solution of silver nitrate, which is AgNO3. And over time, the silver will switch places with the copper. I should say the copper will switch places with the silver. So the copper switches with silver. Again, these are both cations when in ionic reactions. And so the copper ends up pairing with the nitrate. So this is what we call single replacement, because we have a single element by itself and then a compound, and either the cation or the anions will switch places. And so always remember, if you were to see this equation by itself, this just the reactants, you could finish the products. If you knew it was a single replacement, you could figure this out, that it's single replacement just because it's set up this way. Always remember, when you rewrite the products, you always have to balance the charges. So we assume that this is Cu plus 1 here, but if this was like copper 2 plus, then you would have to balance this as CuNO3 2. And then you'd, of course, have to balance the entire equation. So just always keep that in mind. Okay. So then we have double replacement. So double replacement is kind of like single replacement, except it has two compounds. So that's why we say double. So we're switching, we're again, either switching a cation with a cation or an anion with an anion, and we're ending up with two different compounds. This is happening mostly with ionic compounds. It can also be an acid and base reaction, is typically a double replacement reaction. So in this case, I write this as A, B, C, D. So when I'm saying the formula here, A, B, C, D, you can label these A and B. So nitrate, I treat it as one entity because it's a polyatomic ion. So AB and then CD. And then either your A and your C switch or your B and your D switch. Either way, you're going to end up with the same compounds in the end. So in this case, I'll switch the anions. So I'm going to switch the B with the D. And I'll end up with AD, so that's PB and I, and notice how this turns into PBI2, because in this one, PB is a 2 plus charge, and we see that because we have two nitrates here. So remember, nitrate is a -1 charge. So if we have two nitrates, that means PB has to be 2 plus. And so the reason I draw attention to that is just reviewing ionic formulas and naming. And so over here, we assume PB is still going to remain 2 plus charge, and iodine is 1 minus. So that's why we pull the 2 down here to do PBI2. And then we have KNO3. So K is +1, NO3 is 1 minus, so we can keep it just as KNO3. And then of course we balance the entire equation with the coefficients here. So double replacement, again, if you see just the reactants, you can kind of predict this is double replacement because it's two ionic compounds. So this is very cut and dry. Oh, okay, two ionic compounds, really the only thing they will do is they will swap either, like we say, swap partners. So they will swap either their cations or their anions. Just always remember the products must depict proper ionic formulas. So you must have a cation and an anion in both of these compounds as well. If you switch PB with K, or sorry, if you switch PB with I, technically, then you would have two negative ions together. Like you'd have K and PB, and then you would have I and NO3, which doesn't work because I and NO3 are both negative, they're both anions, and K and PB are both positive. So you always must have a positive and negative at the beginning and at the end in both compounds. Okay, and then the last one is combustion. And I find that most students are, they really get scared with a combustion reaction, but it's actually one of the easiest ones to write. All you need to know is the carbon compound in the beginning, and every combustion reaction is the same after that. So, kind of. So you have a carbon compound, which is C and H and sometimes O. Sometimes there's a couple of other compounds in there, but most of the time in AP, they say C and H and sometimes O. So this is typically a fuel compound, like we're talking methane, ethane, butane. These are things that we use as fuel. Think of like lighter fluid, what you put in a lighter, gasoline. So all of these are combustion reactions. And so what we do is we combust a fuel with oxygen. So O2 is always a reactant. And then always, always, always our products are just going to be CO2 and H2O. So combustion reaction is the same every time. It's the easiest to write. When you balance a combustion reaction, it's kind of like the same strategy every time. You can start with your carbon compound and work back and forth. I'll get into balancing for a second. The only thing to watch out for is typically in AP, these will be word problems. It'll be like, write the combustion reaction of ethane or something like that. They'll give you the formula for the carbon compound. You don't have to know those, but the only thing you have to watch out for is the wording, because sometimes combustion reactions can be incomplete. So if they're incomplete, that means they only produce CO instead of CO2. Now, if it doesn't say anything, if it just says write the combustion reaction, you assume it's complete. It will say specifically write the incomplete combustion reaction or something like that, in which case you would have to remember, okay, that's CO. And so the reason that, and this is, I always talk about this in my classes, the reason that sometimes the combustion reaction produces CO instead of CO2 is because there's not enough oxygen. So this is why we say, like, don't start a gas grill in a garage, don't start your car in a closed garage, because essentially when you turn your car on, you're starting to combust the gasoline in your car. And if there's not enough available oxygen in your garage or wherever you're starting it in a closed, confined space, there will not be enough oxygen to completely combust the fuel. And so you'll end up combusting CO instead, which is carbon monoxide. So that's not, that's dangerous. So this is why it's always good to, whenever you're combusting fuel, whenever you're turning your car on, whenever you're lighting up a grill, running a generator, we see this a lot during hurricane season in Florida, it's always really important that you're doing this in the open air, because carbon monoxide is an odorless gas and you won't know that you're breathing it in until it's too late. So, and now you know why. So you have to have enough oxygen to make sure that that fuel is completely combusted into carbon dioxide. Now, you don't want to be breathing that in either. That's not great, but it's a little better than carbon monoxide. So again, combustion reactions, all you really have to know to complete a combustion reaction is the fuel type. So CH4 in this case is methane gas. And so if I know methane is being combusted, then I know it's CH4 plus O2, always O2 in the reactants, yields CO2 and H2O. And so every single time a combustion reaction will be like that. If for some reason there's another element in here besides C and H and sometimes O, the question will say like the other product that's being produced. All you really have to know or be responsible for is knowing the basic combustion reactions, which is this. And I'll tell you a trick, or I'll show you a trick in a second on how to balance these, because sometimes they're a little complicated. Okay, so moving on, writing and balancing equations. So we're basically just going to do some practice. And within this, I'm going to go through and I'm going to go write this out. And this is like my way of kind of reviewing, naming and writing compounds. So I'll write this out and then the answers down below here so we can check. So solid zinc. So when we write when we write and balance equations, we always make sure that we try to include states when appropriate or when we can. And then we balance them at the end. So we try to include states. We want to make sure our ionic compounds are, I say balanced, but we want to make sure our ionic compounds are correct in that the charges are balanced out or the charges are crisscrossed and simplified. And then we want to balance our overall reaction in the end to make sure we have the same amount of elements on both sides. So solid zinc. So zinc on the periodic table is Zn. And I'm going to abbreviate this as solid. Because it's a solid, we assume it's not an ion. So solids are not ions. Ions only form when a compound is formed. So solid zinc reacts with hydrochloric acid, which is HCl. If it's an acid, we assume it's aqueous. Now, acid naming rules, just as a really brief recap, hydro in the name means there's no O. So I always tell my students, if you're naming acids, just ignore the hydrogen in the acid for a minute and just look at what it's attached to. So chloric. So hydrochloric means there's no O and you're looking for chlorine, and then attach an H to it. And then you always look at the charges in acids to make sure they balance out. So chlorine is -1, H is +1, so they're good. It's just HCl. So zinc reacts with hydrochloric acid to form, so this means arrow, zinc chloride. So zinc chloride is an ionic compound. So we have to think about the charges of both of these to make sure that they balance out, or to make sure that this compound is correct. Zinc is one of those exceptions on the periodic table that's always a +2 charge. So I'm going to write this just so you can see how we write these compounds. But when you actually write a compound properly, you don't include the charges in the final equation. But zinc, you should take note of this. It is a transition metal, but we don't use the Roman numerals with zinc because it's always a +2 charge. So just write that out. Every time we've encountered zinc, it's been a +2 charge, like that's its oxidation state, meaning it always loses 2 electrons. So we just say zinc is +2. So if zinc is +2 and chlorine is 1-, we just pull this charge down here and we get ZnCl2. And the 1 comes down here, but we don't write the 1. So this is, again, writing and naming ionic compounds. So zinc chloride, and then hydrogen gas, which would be H2. Remember that, oh, and then zinc chloride is a ionic compound. So we just write aqueous, and then hydrogen gas is G. Remember that H2, so the diatomic molecules, I say Brinkelhoff, BRINCLHOF. So 2, 2, 2, 2, 2. So remember that all of these molecules, there's 7 of them, will always appear in pairs when they are gas. Most of them are gases at room temperature. So if you see them by themselves, like hydrogen, you're never going to see H just by itself. It's always going to be H2, unless it's an ion, unless it's ionized, which is totally different. So typically, if you see any of these like hydrogen gas, chlorine gas, oxygen gas, you know that this is a diatomic molecule. So you write it as H2 or Cl2 or whatever it is. So just really briefly, diatomic molecules. So here's our equation. Zinc plus HCl yields ZnCl2 plus H2. And so the last step is, I've got my states in here. The last step is balancing the entire equation. So I typically start with the most complicated molecule, which I say is this one here, ZnCl2. And I kind of work back and forth. I don't make a chart, but you might want to start out doing that if that makes you more comfortable. You can make a chart like, okay, over here there's 2 H's, there's 2 Cl's, there's 1 zinc. In AP, it's kind of like a time crunch, so you have to be really proficient at balancing equations and being able to just kind of go back and forth. So I start here and I say, okay, well there's 1 zinc and 2 Cl's, but over here there's only 1 Cl. So I know I'm going to have to put a 2 here to make 2 Cl's. But now I've just changed my H as well. So now I have 2 H's. So I'm going to check back over here. Oh, that balances out. There's 2 H's there. And then my zincs are good. So now I'm good. I've balanced this equation. So let's check. Zinc plus 2HCl, ZnCl2 plus H2. And this is a single replacement reaction because we've had a single element with a compound, and the zinc and the hydrogen, sorry, I should go, zinc and hydrogen have switched places. So the zinc and the hydrogen, when in ionic form, are both cations or both positively charged. So they can switch, and then zinc bonds with chlorine. And then notice we have 2 chlorines here because that's the way the charges work with this ionic compound versus 1 chlorine here. But we have the 2 here to balance out the equation. So now all of our elements are equal on both sides. Okay. Next one, so solid sodium oxide reacts with water to form sodium hydroxide. Okay, so what type of equation or what type of reaction would this be? Right off the bat, if it's going from 2 things to 1, you might guess that it's a synthesis reaction. So let's just check and see. So solid sodium oxide. So sodium oxide is an ionic compound because it's a metal and non-metal. So sodium, I know, is Na, and when it's in ionic form, it's a +1 charge. And all of this, I'm not really going over this, But all of this is on your, it's a pattern on your periodic table. So when you learn this or review this, you'll probably remember the charges and everything, but they're basically like +1, +2, skip over the transitions, +3, ±4, -3, -2, -1, and then you're into the noble gases. So that's essentially the groups as you go across the periodic table. That's just in a nutshell. And of course, in AP, it's all about exceptions. So there's a ton of exceptions to that, but as a whole, you've probably remembered these charges or oxidation states from Chem 1. So Na is +1, oxide is 2-. And so if I crisscross these, so I always teach you can crisscross and then simplify, and that's will work for you every time. So if I pull the 2 down, so only pull the number down and the 1 down, then I really just get Na2O. Reacts with water, so we assume this is H2O. And this forms sodium hydroxide. So sodium is still Na, and then hydroxide, remember, is a polyatomic ion. It is the formula OH. Hydroxide is a 1- charge. Sodium is a +1 charge. So we just leave this like it is because they're both +1, -1, so they cancel out. Remember, the +1 means it's losing an electron. The minus means it's gaining an electron. So because sodium has 1 electron to lose and hydroxide as a whole has 1 electron to gain, they combine in a 1-to-1 ratio, and that works out. Whereas over here, sodium oxide, sodium again has 1 electron to gain, but oxygen has 2 electrons. Sorry, sodium has 1 electron to lose, oxygen has 2 electrons to gain. So in order for this to combine perfectly, there needs to be 2 sodiums here to accommodate the 1 oxygen needing 2 electrons from sodium, but they only have 1 each. So this is why, that's kind of like the premise of why we do crisscross. The crisscross method is definitely the easiest and least tedious way of coming to the correct formula every time. Okay, so back to this. Sodium oxide reacts with water to form sodium hydroxide. So this is good. All we need to do is balance. So check again, I look at the most complicated compound, which is like this one over here, I would say, and this is a 2 in front of the Na or behind the Na. So 2 NAs. So I have to fix this one over here and put a 2 here. But then this changes a couple of other things. So this changes the O to 2. So I'm going to go back and double check, but there's 2 oxygens on this side because I have 1 and 2 here. So I'm good with that. And then there's 2 H's now because I put the 2 in front of NaOH. So then I look here, oh, I have 2 H's here. So this is fine. So the equation is balanced. So Na2O, solid, oh, I forgot the states. Solid, and that says solid, reacts with water. Water's usually always liquid or vapor. Typically it's vapor is gas. Typically it's gas in combustion reactions. And then any acid or base we can assume is aqueous unless otherwise stated. So we'll say is aqueous. So Na2O solid plus H2O liquid yields to NaOH aqueous. And this is, like we identified in the beginning, a synthesis reaction. You'll notice these are 2 compounds coming together to form a larger compound, but we can still consider this a synthesis reaction because we're going from more than one thing to just one thing, or we're going from more to less. So that's essentially a synthesis reaction. Okay, so stay with me. All right, so now we have a couple more practice. Nitric acid reacts with barium hydroxide to produce barium nitrate and water. So nitric acid, another acid naming scheme or tip is nitric. So if this does not have hydro in front of it, we assume that there is an oxygen in the acid. So that, remember the acid naming rules. Then we look at what this ends in. So remember, acids are, I always write this mnemonic, adic itis. And this only applies to ones with an oxygen in it. So, which means they don't have hydro. So if it ends in ic, then you're looking for usually the polyatomic ions that end in ate. So you're looking for nitrate because this ends in ic. So this would be, nitrate is NO3, and then you attach an H in front of it. That's literally acids. You're just kind of looking at the root, which is in this case ic, nitric, so change it to nitrate because ic goes with 8, and then put an H in front, and then you have nitric acid. NO3 is 1 minus charge, and H is +1. So these are good. So we leave it like this. Remember, I treat polyatomic ions as one entity, so I don't pay attention to this 3 and the -1. This whole thing is charged to a -1 charge, so I treat it kind of like as an element in itself. Also remember, the only reason I'm writing charges is to kind of show you how I got to this point. You don't need to write charges, and you shouldn't write charges when you're writing the full equation. So HNO3 reacts with barium hydroxide. So barium is Ba, typically a charge of 2+, and then hydroxide is OH, typically a charge of 1-. So in order for this to work out, we need to pull the 2 down, and we need to put parentheses around, that was terrible, around hydroxide, because we have to indicate that there's 2 hydroxides total and not just 2 H's. So we put parentheses around OH, and then we pull the 2 down on the outside of the parentheses. So now we're basically stating there's barium and then 2 hydroxides. And this makes sense because in this case, barium wants to lose 2 electrons, and hydroxide can only take in 1. So you're going to need 2 hydroxides to accommodate barium's 2 electrons. So reacts with barium hydroxide to produce barium nitrate. So this is a acid-base reaction or double displacement. If you didn't know the products, you could still figure out that this is a double displacement because you just kind of identify the first 2 and then switch them. So the barium goes with nitrate. So Ba, now remember nitrate is a -1 and barium is +2. So I automatically did that with my charges. I just pulled the 2 down. So BaNO3 2 and then water. And so the really cool thing about acid-base reactions is they're still considered double displacement. So when you switch the H in the Ba, H goes with OH. So what is HOH? It's H2O. So it's essentially a neutralization reaction, and that's why acid-base reactions are so cool. You can mix an acid and a base, and essentially what you get at the end is you just get a salt and water. Okay, so now we can balance this. Now, balancing this one is a little bit trickier because there's a lot of compounds that are complicated. I would probably start here because I can see that NO3 is 2 here, but it's only 1 here. So because NO3 did not break apart, I'm going to leave it as NO3, and I'm just going to treat it as like one element. So I'm going to put it 2 over here in front of the entire nitric acid compound to indicate now that there's 2 NO3s. But now I've got to fix my hydrogens because I just changed my hydrogen. So now I have 2 hydrogens, but then I also have hydrogens over here. So I have 2 hydrogens here. So I have to fix the hydrogens here to make 4 because I've got technically 4 total hydrogens on this reactant side. So I put a 2 here because 2 times 2 is 4. And so now my hydrogens are good, my bariums are good. How are my oxygens? So 2 times 1, so 2 oxygens over here, and I have a 2 here, which makes 2 oxygens here. Now, I did not count my oxygens here because I already have grouped those into the nitrate category. So I kind of ignore those. That makes it a little bit easier for me to tally up. I'm like, okay, if I can just satisfy my nitrates on both sides, then all I have to do is look at the oxygens from hydroxide and water. And so this should be the balanced equation. So 2HNO3 plus BaOH2 yields barium nitrate 2 plus 2H2O. And then of course the states, again, acids and bases are typically aqueous. And then any salt that dissolves in water, which you probably haven't done the solubility rules yet, but that'll come later. Any salt that dissolves in water, which nitrates dissolve in everything, we put aqueous, and then H2O is typically liquid unless combustion. Okay, solid calcium sulfite decomposes when heated to form solid calcium oxide and sulfur dioxide gas. So I'm going to remember the states this time. So calcium sulfite. So calcium is Ca, it's a 2+ charge, and then sulfite is SO3, and it is technically a 2- charge. So that works out. Again, like I said, you can always crisscross and then simplify. So if you get good at this, you might realize that when you crisscross these, you'll have a 2 and a 2, and if you simplify that, i.e. divide by common multiple, you'll get 1 and 1. So I'm just going to keep it like this, CaSO3. You should be able or get to a point where you can look at this and say, okay, these are the same charges. I'm just going to keep it as CaSO3. So calcium has 2 electrons to give up. Sulfite has 2 electrons to take in, so they work perfectly as a 1-to-1 ratio. All right, so calcium sulfite, and this is a solid, decomposes when heated. So decomposes usually means aero, so that means it's going through a chemical reaction, it's breaking apart. Remember, decomposition breaks apart, and it forms solid calcium oxide. So calcium and then oxygen. Again, ionic compound because it's metal, non-metal. Calcium is 2+, oxygen is 2-. So I'm just going to leave it as CaO because they work 1-to-1 ratio. And then sulfur dioxide gas. This is the first covalent compound that we've encountered. Covalent means non-metal, non-metal. So sulfur and oxygen are both non-metals. If you're dealing with a covalent compound, meaning like that little tiny square in the upper right-hand side of the periodic table, like that's where all of these come from, is all the non-metals. You just completely ignore charges because these are sharing electrons. So these are actually easier to name and write because you just look at the name. You will see a prefix in the name. So sulfur means there's 1 sulfur. Dioxide means di is 2. There's 2 oxygens. So we don't even pay attention to the charges in covalent compounds. The only time we look at charges is ionic compounds because they're exchanging electrons. Covalent compounds are sharing, so they're not actually becoming charged because they're not technically losing or gaining electrons. They're just sharing them. So we just look at prefixes to name these. Okay, and then the last step for this is balancing. So if you look at this, there's 1 S. I can't just group my SO3 into 1 because it changes over here and becomes SO2. So I've got to actually break everything down and look. So calcium, 1 calcium, 1 S, 1 S, 3 oxygens, but there's 3 oxygens here because 2 + 3, so it's good. So then the final one is CaSO3 solid, yields calcium oxide solid and sulfur dioxide gas. And this is a decomposition. We can tell because it's just 1 compound to start with, but so all it can do is basically break apart, but it also tells us it's decomposition here. Okay, and the final type of reaction is combustion. So in a combustion reaction, you should get to the point where you can just write the entire combustion reaction as long as you know it's complete. So it tells us it's completely combusted as long as you know the fuel type. So in this case, this is ethane, so C2H6. So in a combustion reaction, these are the easiest to write because they always involve the same exact thing. Now this is gaseous ethane, so I'm going to write this as gas. The reactant is always going to be O2, and the product, as long as it's complete, is always going to be carbon dioxide, and the byproduct is water, H2O. So every combustion reaction will be the same. You will just have a different fuel type. So oxygen is going to be a gas, carbon dioxide is also a gas, and typically in combustion reactions, the byproduct of water comes out as water vapor, which is a gas. So balancing combustion reactions is the same method every time, but sometimes you will have to use a fraction. So I'll show you what that means. So you can always start with the carbon compound or your fuel, which is C2H6. So always start with your carbons first. So there's 2 carbons here. So the only way that I can fix the carbons over here is by putting a 2 in front of CO2. So now I have 2 carbons, but I've messed with my oxygens. Now, I'm not going to go back and fix my oxygens over here because I still need to balance the hydrogen. So in every combustion reaction that you do, you should just start with carbon, then go to hydrogen. Always leave this O2 for last because this is the easiest to manipulate in your equation. And so you leave it for last because you can basically make it whatever you want. Now the 2 makes it a little bit tricky, and I'll go over that in a second. So H6, so over here we have 2. So what times 2 is 6? We say 3, so we put a 3 in front of here because that's the only way we can change the H. So now when I look at this, I'm like, okay, I have to change my oxygens now. So now I'm going to tally up my oxygens. So I have 4 here because 2 times 2 is 4. And then I have 3 here, which is not great because this is an odd number. So 4 plus 3 is 7. So 7, how do we make this 7 when this is a 2? What times 2 is 7? So in this case, I would recommend a fraction and then fixing the fraction and then getting rid of it. We can never put a fraction in and leave it, but we can put a fraction in as a really quick way to get to the right answer. So if I put a 7/2, because what times 2 is 7? Well, 7 over 2, because 2 cross out the denominator and you get 7. So 7/2. So as a snapshot, this is a perfectly balanced equation, but we can't leave the fractions in the equations. So we have to basically eliminate the fraction by multiplying the entire equation by the denominator of this fraction, which is 2. So then we get 2C2H6, I'm not going to write the states, plus, so 2 times 7 over 2 is just 7. So this is why we eliminate the fraction, or this is how we eliminate the fraction, is we just up everything by 2. So 7O2 yields 4 CO2. So again, you're not changing the subscripts, you're just changing the coefficients, and then 6 H2O. So did we get it? Okay, 2C2H6 gas plus 7O2 gas yields 4 CO2 gas plus 6 H2O gas. So this works. So again, sometimes you won't have to do this. Like sometimes it'll work, you don't have to use the fraction, but typically combustion reactions, it's like a 50-50. You're gonna have to use the fraction method. The fraction method is not that bad. It usually just involves doing something, whatever you need this number to be, over 2, because it's usually O2 that's the difficult one. And so 7 over 2 or whatever it needs to be, and then just up everything else by 2 and then get rid of this fraction. So fractions are your friend. They're easy to, they're an easy way to get to the balanced equation. Okay, so writing and balancing equations, we've been through types of reactions. We briefly went over how to write and name ionic compounds. This will be good review for you. We talked a little bit about covalent really quick. Carbon dioxide, remember carbon and then dioxide. This is a covalent compound because it's 2 nonmetals. We talked about balancing. And so the last thing we're going to do tonight is stoichiometry. Now, this is probably one of the hardest things in chemistry, which is why I included this in here, because you must be proficient at this in AP. AP it has a lot of math. You technically don't have to do a single math problem on the AP exam to actually still do really well on it. However, it's good to know this math. Like it's good to be able to do dimensional analysis. So this is piggybacking off of the second webinar that I did last week with dimensional analysis, and it's kind of just adding to it. Stoichiometry does not have to be difficult. It's basically just organizing your units properly and then filling in numbers. That's kind of how I do it. But it's a way to go from grams of one side of the equation to grams of the other. It's basically saying if we have 20 grams of this reactant, how many grams of product are we going to produce? And these are equations that are used in every day in our industries, our chemical industries, to figure out products, to figure out, I want X amount of product, how much reactant do I need? So we use these equations in real life all the time. So this is why they're important. So stoichiometry calculations. So if we want to go from grams of one side to grams of the other, which is the biggest stoichiometry equation that you'll do, that's a 3-step process. We start with grams of A, which is grams of given, basically. So first we have to convert grams of A into moles of A, essentially. So we do grams of A. So we start by writing grams of A, whatever A is, and whatever amount of grams there are. this is our given. We start out writing our equation like this, and we pull the same unit down to the first fraction to cancel this out. And we always get into mole first because mole is our trading value. So mole's like, if you remember the mole map from Chem 1, always go into the mole first before you get anywhere else, because everything in chemistry can be quantified and related to one another via the mole. So grams of A to moles of A using molar mass. So wherever you're plugging in conversion factors here, you're getting this value from the periodic table, molar mass. So grams are associated with molar mass. Second step is convert moles of the given, so moles that you're starting with, i.e. the grams that they give you, to moles that you want. So this is done via the balanced equation. So mole ratio from the coefficients in the balanced equation. So this is why it's important to know how to write and balance an equation. And then the third, so that's the second step, or the middle fraction. And then the third step is convert into the new grams from the moles. So you've just converted into new moles, and now you have to go back to grams. So because we have, notice the units are crucial here. Grams of A on the bottom. Moles of A, pull this unit down, moles of A on the bottom. Moles of B, pull this unit down, moles of B on the bottom here, and these will all cross out to give you grams of B. So this is how we get from grams of A to grams of B. So I want to know, in a combustion reaction, I want to produce 20 grams of CO2 or something like, let's do a different reaction. Like I want to produce, in an acid-base reaction, I want to produce 20 grams of product. How many grams of reactant do I have to put into that? This is how you would do this. You'd have to go from however many grams you're given, what you want to try, or what's your goal, or what you're given in the equation, and go through the mole using mole ratios and then back to the gram value. And remember, gram values, gram to moles, are always from the molar mass on the periodic table. So this is the bottom number. The molar mass on the periodic table is how many grams of that element are in 1 mole. So everything is quantified for 1 mole. So let's do an example, and then we'll be done for the night. So one example of stoichiometry to kind of get your brain moving again about and remember what is stoichiometry and reviewing that for the year. Okay, so here's our example. Solid magnesium is added to an aqueous solution of hydrochloric acid. What mass of H2 gas will be produced? So we know that that's a product. And produced from completely reacting 28.5 grams of HCl with magnesium metal. Okay, here's a good example of this. Does not give us the other part of this equation, but you'll notice H2 is not the only product that is produced here. So the first step to every stoichiometry reaction, if it's not done for you, is write out and balance the equation, because that tells you your recipe, basically, your ratios of all of your elements and your moles. So what type of reaction is this, or does this look like? This is a single element and a compound. So you might guess that it's a single replacement or displacement reaction. So Mg is positive, H is positive, they basically switch places. So the H is going to be by itself, which remember, by itself, H is a diatomic molecule, so it's H2. And then now our new compound is MgCl and then 2, because Mg is technically 2 plus and chlorine is 1 minus. So I just pulled the 2 down here. So MgCl2. Okay, so that's why this is important, to know how to recognize the types of reactions that you're dealing with, because sometimes they don't give you the other components. And why do you need this? Because you have to be able to balance the entire equation so that you can see the ratios of coefficients. So MgCl2, I'm going to start with this compound because this is more complicated. I'm going to fix the chlorines. So there's 2 chlorines over here, so I'm going to put a 2 in front of HCl. And then this makes 2 H's as well, but that works out here. And then my Mg's are fine. So I'm going to delete my annotation so that you can actually see the actual equation typed out. That's a little bit more clear. So here's our equation, which is the one I just wrote. And now we're starting the actual stoichiometry. So first step, write and balance the equation. Make sure that the equation is balanced. That's important because you need to be able to look at your coefficients. That matters in a stoichiometry problem. So second step is, again, we're going from grams of A to grams of B. So we read through this again. It says, what mass of H2? So we're trying to find the mass of H2. So what I do, put a little question mark here, and will be produced completely reacting with 28.5 grams of HCl. Okay, so I write up here 28.5. That's how many grams I have. So I kind of outline my problem and I say, okay, if I have grams of this and I'm trying to get to grams of this, I'm going to need to find the molar masses of these compounds. And so I always try to find the molar masses of my compounds first. Then I can just plug everything into my stoichiometry problem. So I look on the periodic table and you're just adding H plus Cl. So H is 1.008 and chlorine is 35.45. So when we add these together, this equals 36.46 grams. That's how many grams are in 1 mole of HCl. And then H2 is just 1.008 times 2. So this is 2.016. I'm rounding these to 4 sig figs. Just to be accurate from the periodic table. You should always use the decimals on the periodic table in AP because that's what they're grading you on the AP exam, is using the actual numbers from the periodic table that they supply to you. Okay, so now because I have these values, remember this is grams per 1 mole. All of these, whenever you find molar mass, you're always looking at, I didn't write grams. You're always looking at grams per 1 mole. So those are your conversion factors that go into your stoichiometry. So now you've set yourself up for success. Now you can just basically plug it in and solve it. So 28.5 grams is your given. And it's really important, like crucial, that you're writing your unit because this basically dictates where you go from there. So because you started with grams of HCl, this is your given. You always pull that unit down to the first fraction. So this is going to be over here, this fraction is going to be grams of HCl. And then every time I'm going from grams to something else, it's usually the mole because everything is in terms of 1 mole. So that's why I say moles of HCl up here. And so in these initial fractions, everything is in terms of 1 mole. So I'm going to plug in this number here. And where did this come from? The periodic table, 36.46, and this is in terms of 1 mole. So in every 1 mole of HCl, this gives me 36.46 grams of HCl. Why are we doing this? Because we're trying to convert grams of HCl into moles so that we can get into hydrogen gas, because we want to get into moles of hydrogen gas so that then we can convert into grams. So the next step is going from moles to different moles. So now, notice my grams of HCl crossed out with grams of HCl. So this unit matters. Now I'm going to pull this unit, moles of HCl here, down to this fraction here. So moles of HCl, same unit, and that, again, units are so crucial in stoichiometry because they tell you basically what to do. You don't have to memorize. Do I multiply? Do I divide? Just use your units as a guide. So moles of HCl, and I'm trying to get to moles of H2. So whatever you're trying to get to in each fraction step, you put on the top of the fraction. So moles of H2. Now, this step, moles over moles, you're looking at the coefficients in the balanced equation. So we look at H2, which is 1, because there's nothing, and then we look at HCl, which is 2. I always put units first, and then I fill in the numbers to make sure that the numbers are in the right places. The biggest mistake I see on stoichiometry is kids trying to do this without the units, and then they mess up. They like put 2 over 1 or 1 over 2. They mess up like this 36.46 they put on the top instead of the bottom. It's like, I know it's tedious to do the units, but you must put the units in so that they guide you on where to put them in each fraction. So plug in numbers here, 1 mole of H2, 2 moles of HCl. And remember, I'm pulling these numbers down from the balanced equation, which is why that's important. And then the last step, now we're into moles of H2. Whatever this top thing is here, that's what we've converted to so far. I haven't done any calculations. I saved those for the end. But if we were to have done those calculations, this is what we would get. So the last step is going from moles to grams. So you'll notice, again, moles of HCl cross out with moles of HCl. Now I have moles of H2. Pull that unit down to the last fraction. And then again, the last thing I'm trying to get to is mass of H2, which is grams. So because I've gotten into the mole of H2, I can now get to the gram of H2. So you cannot go from grams of one substance to grams of a different substance without going through the mole first, because the mole relates to the balanced equation, which is your balanced stoichiometry relationships, like relationships between each other. It's basically like your recipe. Okay, so moles of H2 cross out with moles of H2, we're left with grams of H2, and we get this number, the 2.016, from this number here that we calculated in the beginning. So this is why I say it's really helpful if you just you kind of outline your problem. You write this is what you have at the top, this is what you're trying to find, this is the molar mass. So outline, because you don't really need to find the molar mass of these, those don't even matter in this equation, it's just superfluous information. So just outline or underline what you need to know. Write down your conversion factors first, then you can just plug everything in once you set up your units, and then literally you solve. Now, this is the other hard part for students I find sometimes, is how do we solve this problem? So I recommend in all of your math problems in AP, try to keep your intermediate steps in the calculator. Try not to round between each step, because that will just mean your answer is going to be off a little bit more. So when I put this into my calculator, I say 28.5 divided by, remember, you've crossed out all your units, so don't worry about your units. You're just looking at numbers right now. So 28.5 divided by 36.46 divided by 2 times 2.016. So if it's on the top, you multiply. If it's on the bottom, you divide. I do all of that, I would do 28.5 divided by 36.46 equals, and then divided by 2 equals, and then times 2.016 equals, and then I round that number to 3 sig figs, because this is the smallest number of sig figs here. These ones, the coefficients I don't look at for sig figs. They're like an infinite number of sig figs. I look at this number here, which is basically the number given to me in the problem, and I look at, okay, that's the least amount of sig figs that I'm rounding to. The other way to solve for this problem that I find some students think or take this easier is just imagine this number is over 1, and so basically just divide your entire problem by numerator and denominator. So just do 28.5 times 2.016 equals whatever that number is, and then 36.46 times 2, and then I'm crossing out the 1 because times 1 is irrelevant. And then whatever this equals, and then do numerator over denominator. I find that that's a lot easier sometimes for some students to do. So all in all, you can check this. It should equal 0.788 grams. So I'm rounding this. I think this was 0.787 something. I rounded this to 0.788 grams of H2. So this is the one and only last standing unit that was here that we didn't cross out. So again, the unit at the top of the fraction at the very end is the unit that you're trying to get to. So you can kind of set everything else up equal to that. Okay, and again, grams of A, this is what you started with. This is the molar mass of A. This is the mole ratio of B over A, or A over B, depending on where your units are. B over A in this case, because we're trying to get to B. And then this number is the molar mass of B. So these are where all these numbers are coming from, and this is the full stoichiometry, grams to grams. In AP, there are many different types of dimensional analysis. You might just go from grams to moles of one substance. You might go from grams of one substance to moles of another substance, which would basically be stopping here. You might go from moles of one substance to grams of another substance, which would basically be starting here and stopping here. So it's important to note, in the problems, and that's half the battle is reading these problems in AP, but it's important to kind of note where you're starting, where you're stopping within this stoichiometry. But this is the entire stoichiometry, grams of one substance to grams of another. So this would be the longest one with all 3 steps. So I felt it was probably the most pertinent to go over, just to kind of jog your memory about last year, or I guess maybe introduce you to this if you didn't see it last year. So I'm going to check the Q&A to see if there's any questions. And if not, then I wish you luck in AP, and I tutor AP quite a bit on Wyzant. It's probably one of my most sought after subjects. So I've been a teacher in AP for a long time. And so I try to cater my lessons to really like how to do well on the AP exam, and obviously in the AP class, because it's quite a bit different than honors chem. Just the way you answer the questions and in your explanations and everything else. So it's important to go through this. It's important to review this. And I wish you well in your AP endeavors. So I don't see any questions. So have a good night, and Wyzant will email you a copy of this lesson, and it will also be on YouTube.